In this video, I review a couple of formulas that give the speed of sound in different materials. Now, don't worry, we are not going to derive these formulas. You only need to know how to use them. Right? The first one gives the speed of sound in a fluid, and it is equal to the square root of B over rho, where B is the bulk modulus of the material in units of pascals, and rho is the density of the fluid in kilogram per cubic meters. Now, for the speed of sound in solid, the formula is quite complicated because the speed of sound depends on direction of propagation of the sound in the solid. It depends on the crystal structure of the material and so on. And if you take upper division solid state physics, we will review this in more details. But for this class, we introduce a simplified formula, which is valid for a solid that has the shape of a long bar. So it is almost like a one-dimensional solid. And in this case, the speed of sound is given by the square root of the Young modulus divided by the density. Again, the Young modulus is a quantity in units of pascals, and rho is the density in kilogram per cubic meters. For a gas, one can use the same formula as for a fluid, but because the bulk modulus and the density depend on the pressure and temperature of the gas, we can use another formula where V is the square root of gamma or T over M, where gamma is the ratio of heat capacities. We will come back to this quantity in the chapter on thermodynamics, but for now, you can just admit that this is a number. R is the gas constant. R is 8.314 joule per mole per Kelvin, and T is the temperature in Kelvin, and M is the molar mass in kilogram per mole. Now, I cannot say this enough, right? This is the number one mistake by people using this formula. The molar mass is often given in gram per mole, but in this formula, you need to convert it to kilogram per mole, right? So every time there is a lot of mistakes here, so try to remember this. Now, let's discuss this formula with examples. So the speed of sound depends on the density rho. So if you decrease the density, you expect to increase the speed of sound. So check out this table here, which gives the speed of sound in different materials. You can see that the speed of sound in helium is larger than the speed of sound in air, and this is because helium has a lower density than air. And similarly, the speed of sound in aluminum is larger than the speed of sound in lead, again because aluminum has a lower density than lead. But density is not the only factor. You can see from the values in this table that the speed of sound for solids is in general larger than the speed of sound in liquids or gases, right? Even though solids have higher density. And this is because the speed of sound also depends on the bulk modulus or the Young modulus. And these quantities vary a lot between solid, liquid, and gases, right? So because the bulk modulus or the Young modulus is much larger for solids, the speed of sound is larger in solids, and so sound waves travel faster in solids, right? You probably have seen this in movies where the character is listening close to the track to hear if there is a train coming, right? And this is because the speed of sound in solids is faster than in gases, so the sound travels faster in the rails than in the air. And so apparently that is true. You can hear a train approaching, right? According to the Association of American Railroads, an approaching train can be detected by as much as a mile away, right? Provided that no other force is acting on the tracks. Now, of course, nowadays trains are electric, so you could get electrocuted. So please don't do this, right? Safety first. You also see from this formula that the speed of sound depends on temperature. And this is the reason why musicians warm up their instruments at the beginning of a concert, right? Of course, they know how to play, right? They don't need to warm up, they are ready, right? But the instrument is not, right? The musician, they blow air inside their instruments, and this way the air temperature inside is at the same temperature it will be during the entire concert,